Kalispera. So thanks for coming here. So one of my missions is to keep you a little bit alive after lunch. I will do my best. So the work that I'm doing, I'm a mechanical engineer. I studied mechanical engineering in the University of Patras. I did my PhD there, and then in 1989 I moved to EPFL when I worked on the group ICT for Sustainable Manufacturing until last May. Since last May, I'm working with the University of Oslo, continuing my career, my work on this topic, as I will explain to you, which is becoming now mature. When I started this 20 years ago, it was not so, but it became mature thanks to the work that you are doing, creating the devices and the architectures and the systems and the software that make Internet of Things happen. So I will try to explain what I mean by that. So first of all, why we are doing all these things. So there is always an economical, societal, and environmental impact of our activities. And I think you know now that we are moving from this paradigm, economic paradigm, which is linear economy. That means when we extract all the materials and all these funny things that help you also to create the funny hardware that we are doing for Mother Earth. And then we transform this material to take the forms that are functional, and we use these components to create useful things like cars, for example, here. But all things in life, including cars, including what you are doing, and including ourselves, we have a certain life, and then we arrive to an end of life, and then life continues. And particularly with what we are using to create the components and the elements that allow us to have the quality of life that we enjoy, all of us, at least in some societies. So we have to think how to take care of them. Not all of this to become waste, but make it more sustainable. And let's say we have some tools to do that. So these are the 17th Sustainable Development Goals that all companies and organizations have to respect to some extent, or to the maximum that they can. And as you may see, some of them, they have to do with industrial application as well. For example, the SDG 9. So we are working, and many of the companies that are participating here and are sponsoring this event, so towards this model of circular economy, where we try at its phase of the life cycle, from the extraction of material to the end of use, to at least learn from what we are doing. So we gather information and use efficiently and effectively this information to optimize and improve things, but also reuse and recycle useful material and redo things with the same material. So this maturity that we are arriving today, I believe is, to a good extent, is due to the advances of technologies. We called at that time, so 20 years ago, emerging technologies that helps to produce what we called also at that time product-embedded information devices, sensors mainly, memory chips, microprocessors, ID devices, such as RFIDs, and communication devices. All the technologies, communication that they help to implement Internet of Things applications, which is the concepts of this, the content of this, the topic of this conference. And these devices, product-embedded information devices, as I would like to call them, so they allow us to develop, when we embed them to products and to systems and assets, to allow these products and assets that have this capacity to develop the capacities that they see, or the properties that they see without within the parentheses, so sensing capabilities, memory capabilities, logic capabilities, identity capabilities, and communication capabilities. And if you think these capabilities are the capabilities that allow us humans to develop our own intelligence. So thanks to that, products are becoming more intelligent and allow us to follow their life cycles. So this diagram here is a diagram of a project called Promise 20 years ago that I had the honor and the pleasure to win and to work on that, on these concepts, which says the obvious thing. So we discussed also with Tom Kachulas yesterday. So we deliver a product together with a piece of information, even a code, serial code. But this piece of information, the information that is contained in this first delivery is continuously improved and documented with new information that gathered from the use of this thing, of this product, thanks to the devices, the embedded devices that are embedded to that, and allow not only this information to be produced, but communicated to other systems or humans that are involved in the life of this product through dialogues, seamless. I hear the word seamless from you, Kushal, before. Seamless communication because it's wireless and the APIs allow this seamless communication, not only between the product and the human, but also between the product and the system or between the product and another product, Internet of Things. And also at the same time, this system, the human or another system, can communicate this information which is gathered through the life cycle with the creators, the designers of the thing. And if you think this thing, so this loop, closed loop of information, creation, designer, delivery, use, service, up to the end of life, there is also always a closed loop of information. But before the era of this fourth industrial revolution, this used to happen between humans. And all the reports and the information and the data were reported manually in papers, classified in files, and forgotten. And so the most common use of this information used to be when there was an accident, and we were trying to find the cause or a failure. Okay? Now this information loops, thanks to the technologies that are developed today, and they continue to improve, these information loops happen instantly and allow this information and data flow between all the life cycles, beginning of life, design and production, middle of life, use and service. Predictive maintenance is part of this, one of the major actual services are of interest for industry, particularly for manufacturing industry, producing goods that we are using in the middle of life. And then at the end of life, we try to do it as efficiently as possible, and extract value of obsolete products and reuse them as much as we can. And then this is the architecture that we designed at that time with the help of SAP, who was among the key partners in this project, Fiat, white goods companies, Caterpillar, Toyota was part also of this project, etc. And this architecture starts with data gathering from product embedded information devices. And at that time, we had only some sensors and RFIDs. Now you have much more. You have videos embedded, so you have in your booth, so very thin things. You have much more data at that time. And then you have here, you may have the edge or the cloud. And the edge is much more efficient to analyze as middleware this data that provides the appropriate pieces of information for business intelligence and business decision support. And this is the RAMI, means reference architecture model of Industry 4.0. And if you think so, this implements also this concept, and the architecture is more detailed, but has the same major elements and layers in what is implemented today. Industry 4.0 is the implementation of all these things from also the beginning of life, so the life cycles, the elements of business, and also the architecture layers from the asset with the PIDs up to business decisions. Industry 4.0, what is it? So it is the era of information. And so Industry 3.0 is the automation with electricity and all these electric engineering devices. And we start to work more with data in Industry 4.0. From my experience, manufacturing companies are somewhere at the beginning of this. So they collect data, they visualize the data, and they try to let human try to use this data by means of visualization or some kind of simulation. So we go more and more some advanced sectors in analytics, data analytics, with predictability. AI is about predictability. And let's say the final objective of Industry 4.0, where we will be arriving soon, is certain levels of autonomy of systems that are produced. Autonomy of machines, autonomy of cars, if it happens, and autonomy of assets. And then this level of autonomy so requires some kind of cognitive capabilities, which means assessing the environment and reasoning and taking decisions that they are able also to act upon it, so to actuate what decisions are taken. So we implemented, so we started in 2004, 2008 with these concepts. And at the end of this project, 2008, I realized that there was no concept or the idea of Internet of Things was not existing at that time. So at the end of this project, so there were discussions in the European Commission about what will be the future of the future of Internet, and then the term Internet of Things was, let's say, proposed, and is here now. And also CPS is Cyber Physical Systems, which is a component that uses also as part of Internet of Things to realize what this allows. So we have these platforms and the Internet of Things and all that stuff. And I think what it mainly allows is all the stakeholders in a value chain. So Tom proposed also this term of value chain, are communicated instantly together. Not only the stakeholders, but the systems used by the stakeholders. And what they do, they share, they exchange, let's say, data. And to take decisions, they transform this data to information. We are able to take decisions based on information gathered, extracted from data. And if we transform information when we have enough information about something, so we transform information to knowledge, which is recorded and used by next generations or by current generations and next generation to create new things. So this now, thanks to this kind of technologies and the real-time availability of data and information, transformed information that becomes available immediately, so this process is very fast and accelerated and efficient. And as engineers, so in the production, when we have the life cycle, we are using always these three elements. So we want to create a product by using resources and applying a process. This is what we do in electronics. So in the beginning of life, so in the design, so the product is the blueprint, is the specifications. So in the production phase is the physical thing. So in the using phase, the product is the product as used and needs services, etc. And at the end of life is the product as recycled or as reused and so on and so forth. And we are using appropriate information from its life, from its phase of the life cycle to improve design or to decide about the end of life or to improve maintenance, for example. These are the logos and names of various projects that we used in that thing. So with these things in place, we have a lot of data, big data that are produced by the sensors that you are applying very efficiently in current products, various types of sensors. So my, let's say, activity is what to do with this data, how to prepare this data in order to make available to decision makers humans or systems to allow them, autonomous systems, to take good decisions. This is what I am interested in now. And then we discussed about data sharing or trusted data sharing. In the link here, there is a report of a community of the World Economic Forum, Advanced Manufacturing Value Chains, where I'm involved of, and I contributed to this report, is how to take the value of the data that is generated by machines or other activities in the manufacturing context. And then data can be used inside the company or between company-wide, if there is a corporation, or cross-company. And at each level, you have various restrictions, various constraints, various rules to respect, of course. And then if you are in your closed laboratory and department, so you may apply basic analytics because you don't know very well what you are doing. And then if your set of data is more complex, you need advanced analytics, you have more data, and we are using more and more what we call AI now, artificial intelligence, whatever you understand by AI, including ChatGPT. This may help to optimize the use of assets within a company or in a value chain, because information is shared and information from one asset may help to optimize the performance of another asset. But as we have already heard, so there are barriers to data sharing. There are technical barriers, of course, so you have silos of information, you have digital levels of maturity in various data provisions, data owners, etc. But you have also non-technical barriers, which is trust-related barriers that they have to do with ownership, with lack of visibility, who is using the data, etc. And there are efforts current that I know, at least in the European Union level, there are efforts to provide solutions to this with the concept of data spaces, where data as products are provided in the so-called data spaces, and there are business operations there to make good use of them and appropriate good use of them. And a basic concept, a basic, let's say, idea that will help in that direction is the digital product passport that has been already mentioned. Now, so this topic, semantic modeling and model-based system engineering, is what was my research in the last year and continues in the next year in new projects. So what to do with big data? So I think we see the limits of machine learning algorithms and deep learning algorithms in various applications. So there are good applications and good results, for example, in image processing, in image recognition, so which has the use to autonomous cars, for example, but there are limits. So maybe you know the anecdote with Elon Musk, who was in front of a Tesla, running against him with a speed, and the car, without driver, and the car stopped. So the car, so what they don't say or what they said afterwards, the car didn't stop because it recognized a human, but because Elon Musk had a T-shirt with a stop sign here. So the camera that you mentioned also, the camera that recognizes signs in the road, recognized the stop sign, and it stopped. So there are various rules to be, various problems to be solved until we arrive to autonomous cars. I believe it will happen, but it will take still some time. So back to our topic, what we do the big data in order to take informed decisions and arrive to what we call now explainable AI, at least in the industrial context. So it is what I will say, I will try to explain to you now. So data, first of all, we have to recognize that our data are available coming from various sources, data sources, captured somehow. They have a value, either numerical or whatever you want. They are applicable and, let's say, recognizable and useful within a given context. Maybe they are not useful in different contexts. They can be transformed to information by applying various types of algorithms. They are interpreted up to the level of knowledge, Of course, and the actual application, the most, let's say, practical and useful application today is the visualization of data. And we can learn a lot by visualizing data. It's more information, visualization, and allows taking decisions. So I try to explain to you what I mean by the meaning of data. As engineers, we have to go to the meaning of data to take decisions, not just crunch the numbers. A simple example here, 38.5, it's a value. It's a numerical value. If you associate, let's say, to temperature, to the heat problem, 38.5 degrees of Celsius is a value of a temperature. If that I can see in the thermometer when I take the temperature of my body. Thermometer is the sensor. Here I have an oven, and also I can measure the temperature of the oven with another type of sensor, another type of thermometer. So in this example, what is the source of data? What do you think? What is the source of this 38.5? The sensor or something else? The body, bravo. This is the body. The source of data is the body. This is the source that creates the, let's say, the phenomenon in the body that allows the sensor to capture the effect of this phenomenon in my body and show it to me. So the sensor is the bearer of what I measure in my body. And in the context of my body, 38.5 means fever, so I have to take action, or stay at home and sleep, or go to the doctor if I have other things, or if I'm afraid that I have COVID or whatever. So in the other context of the oven, if you read in the sensor 38.5, you will never eat whatever you want to cook there. Okay, so different meaning of the same value in the context of my body, different meaning in the context of the oven. So we have to do similar kind of reflection in phenomena, in various types of phenomena when we measure values about humidity, about velocity, about acceleration, in various, let's say, context of the specific object that we are studying. So our mind, it is able to assess the thing that I explained to you instantly. Because we are able to think at the level of temperatures, at the level of fever, we know what is it. So how to tell this thing to the computer? How to make the computer understand what it is about? Okay, so since years, we have this concept of ontologies that started with philosophers. And the first philosopher to start about this concept was Aristotle, with the categories, studying mammals in biology. And this explains also why the first application of this thing in the informatics of ontologies was in the bio sector, because there you have taxonomies, easy to understand. In the engineering domain, it's more complex. So again, some years ago, there is a more and more effort invested by research and also industry to structure the data with their semantics. They are trying to capture some of the meaning of the data in computer models that are implemented in ontology. This is the schema. This is the diagram, the graph of an ontology, that what it says mainly. So we have the entities. So this is the instance, the value, which is a body temperature. It may be an oven temperature, but both temperatures are a certain quality. Temperature is a quality of my body, if you want to do it. It's an attribute of my situation today measured in temperature. And then this body temperature is to the human body or to the oven, which both are material entities, higher abstraction levels. And also this is captured with temperature, with a temperature sensor device, which is a sensor, which is an object, which is again a material entity. So we have techniques to allow computers to structure the notion of the data that we want them to have with this kind of tool. So this is the graph, but there are languages, standard languages, OWL, for example, that allow the computer to record in this language what you see here. And this allows to information that is coming from silos, which are heterogeneous and from various sources in various forms, to be organized in semantics, in ontologies, using not only the data and what we know about data as we capture them, but knowledge about the domain. So when we build ontologies, we talk to experts, to subject matter experts. And we define together, we, knowledge engineers or ontologists, we define together the data itself. There are relations. Also, you saw before that there were relations between the entities. And these are ontologies are the schema to create what we call knowledge graphs, which are linked data that belong to entities and linked together with the relationships. All the success of Google's and Facebook and YouTube and these funny searches that we do instantly are started using this kind of technologies. And this, when we have what we call semantically enriched data sets formed in knowledge graphs, we may apply new generations of ML algorithms or data analytics to create informed reports on purpose and within the given context. This is happening now. There are also small companies that they start implementing these ideas. This is yet in the context of engineering, industrial context, and the life cycle. So with my friend Barry Smith, who is a philosopher and ontologist, we identified 3 categories of entities that are relevant to this domain. So first of all, the material entities, where we act and we produce, are the real things. We take decisions on these actions about the material based on information. So we have information entities, and we follow a process, which is a workflow all along the life cycle from design to end of life. There are various, of course, specifications behind that, but you can associate a lot of things using this way of thinking. And based on these observations, and the other observation that we observed in 2016, that many organizations, and particularly industrial organizations, they were producing ontologies and knowledge graphs, but without following any standard and any particular methodology. So it was intuitional and ad hoc, with the result that their ontologies were not interoperable. They are not using not the same vocabularies, using different vocabularies. And we created a community, Industrial Ontologies Foundry, where we try to create ontologies, first methodologies to create ontologies, and then ontologies that respect a certain hierarchy from a top level, from a top level. Basic formal ontology is a small ontology with basic concepts of like continuance or time or process and this kind of, I don't go to details. And then domain ontologies that are universal, about universal knowledge, and some subdomain ontologies. For example, you have material ontologies and you need an ontology about stainless steel or gold or whatever. And these are used by industry in application ontologies which remain private. So the objective of this community is to create ontologies that are going to be standards to be used by any industrial company. And we have delivered so far the BFO, which is an ISO standard, the IF core, which is a domain, let's say, middle-level ontology in the manufacturing domain. And now, recently, we have also an ontology about supply chains and an ontology about maintenance that are delivered and are available in GitHub. And also in Europe, just now, there is the end of a project, autocommons.eu. It's a CSA's, Coordination Support Action, where we created a community to, along the lines also of IOF, the previous community that it is already in a certain level of maturity with members, industrial members, etc., to create the tools for practitioners to develop this kind of techniques. among the first supporters from the very beginning was Airbus and Dassault Systems. And other companies are joined and are joining and following these ideas. So based on this, so then we thought that no, we have to cover the life cycle. So this is a system. If we want to do it systematically, we have to use and follow a model-based engineering. We have to start with a model of the system. So using standards, we follow the famous V approach of model-based system engineering that also helps to go to the next step. I will explain you why we do that. So this is one of the definitions of the 5 element definitions of a digital twin, when you have the 2 basic elements, of course, so the physical entity and the virtual entity that are sharing data using communication connections, and what to do with that. So you develop various types of services, analysis, simulations, whatever you want. So the thing is that these digital twins, they are going, or must, or they do, the various types of digital twins cover parts of the life cycle, from design to operation and then back with the end of life, etc. There are heterogeneous details. There is not one digital twin that covers everything. So we have to connect them together. How we do that? So this is my last, let's say, period research. So we propose this concept of cognitive digital twin, where always we have the physical part, the physical entities, and the various components of these physical entities and the life cycle of this are modeled using a system model, using models-based system engineering approach. We have a system model of the entity or the physical asset that we want to analyze. And in these physical assets, we have all the sensors that we are able now to embed, and we collect data. So this data, we organize them in ontology, using ontology in entities of the physical asset. So upon this, various components of this system, in order to study, to design, or study the operation, or do maintenance, etc., from time to time, we apply digital twins. And there are various instances of digital twins that we run along the life. So how to collect and explore the data that we collect from these virtual instances, from simulations, from calculations, or whatever we have. So we structure them again in, in another ontology for the virtual part of data, and we link them, the two, in an integrated knowledge graph. When we have data from the sensors, from the physical assets, and from what we are able to calculate and simulate in the digital twins. And upon that, we are able to apply modern AI, I would say, techniques to take decisions, to help the decision support. So also, we need also to govern this thing. So also all these operations on the cognitive digital twins, and there are various, these are results of research projects like the ones that you see here. So there is a concept of hybrid twin, when you combine data and physical models, when we have mathematics, and we know how something operates, it would be a pity to not use this kind of knowledge. And all these are elements of cognitive processes. What we can do with data, what we can do with knowledge that we gather from mathematics and other phenomena that we allow us to control the system. So we captured all this in a kind of framework from the, as you see, from the real space and from the virtual space. We have them in graphs, and we applied that this one here in one application together with Airbus in the project called Quality that terminated a few time ago. So we applied the principles. The case was at the beginning of life. So the case is how to assemble together two components of the fuselage of the aircraft, where you need high precision. So the designers, they create the design, and then the manufacturers, the industrial engineers, they have to decide how this is going to be manufactured. And they have to, before starting manufacturing, they have to evaluate various alternatives and take decisions. So we have the requirements, as I said. So we have to organize the architecture of the manufacturing system, how it is going to operate. And then we apply simulation techniques, 2D and 3D simulations for the final decision. Then there are trade-offs that are done, and then a decision is taken. So as I said, so the thing is to put together two pieces of this kind of things. And you see the dimensions, so we have to take care of ergonomics and other type of information. So at Airbus, they have industrial system engineers that they design all this system in order to take informed decisions. And we help mainly here to capture the knowledge and the data in this kind of semantic models with some kind of system engineering that are designed, and then the decisions are taken by simulation and trade-off of the results of the simulation. This is the tool set, and they follow the system engineering standard approach as it is the current practices. And the tools that have been used for the simulation, it is a Python tool for the 2D simulations, comparing and evaluating the various manufacturing scenarios. And a tool of visual components. This is a company with software to do 3D simulations. And the trade-off is based on a comparison of visual analytics and visualization of the results of analytics. This is how we produce the semantic model from the requirements and from the use of experts. That is captured by using the various elements of ontologies that, as I mentioned, produced by the AWF community. We try also to classify the entities that you see here, so manufactured product, resources, etc., in these basic elements of manufacturing. So you have material, you have resources, you have functions that have to be realized, you have to respect quality, and you follow a process. So we try to organize as much as we can the entities that are useful to make decisions. So these are various details, how for example, here is the application ontologies, when we have specific information about specific assembly operations used by Airbus that are not reported in higher level ontologies. And at the end, what we have is a knowledge graph, which, as you see, there are tools now that they help to visualize knowledge graphs. That means all the entities that are linked to each other by clustering them. So you see, for example, here, I'm not doing that. So here you may have the entities that are relevant to a particular operation or to a particular material. And you can easily see what you have in your database. And we follow the flow of structuring the operation until the final end, which is a decision structure matrix, which allows engineers to take decisions. So I go a little bit fast to be on time. So and we tested that on data coming from Airbus engineers in the design, not this airplane, but an airplane which is under design, a small part of it. I had a video, but unfortunately cannot be played. There are some no, I think it will not run. No. So sorry for that, but I don't know if I can make the video available somehow. It is available on YouTube. You have it here. So you can view this video there. Here are the, let's say, so far, what we observed in our projects, the enablers of this, what we call cognitive digital twins. So the knowledge graphs and the models and specifications, the life cycle component. So if it will run in the edge, the fog on the cloud. So the trend is to run as much as you can on the edge, as you know better than me. Consider also business operations and governance, why you do that, how these are linked, and all that stuff. So, of course, there are the main challenges that I see now as I learn more and more. So the thing is with the standards. So these technologies will not become, let's say, practical and used by all communities if they are not becoming, they don't arrive to a certain level of maturity to become standards. This is in progress. So we are approaching more and more in that. So the communities that they work already with knowledge graphs and ontologies, they understand that they have to work with others and follow standards, and this is going to happen. By the way, I don't know if Gartner, you know the Gartner group, so they say that by 2025, 80% of the data will be stored in knowledge graphs. 2021, this was 10%. So in 4 years, they foresee that industry will pass to knowledge graphs very fast, because this is becoming more and more mature and cheaper to manage and store, and more applications are available. But this will not become, let's say, but knowledge graphs, the way that are produced today, are created based on instances, not on ontologies. And I'm afraid that these knowledge graphs will be revisited based on good scientific foundations. And let me finish with what we are doing now. So when I'm in University of Oslo, my colleagues there are active in the oil and gas Norwegian ecosystem, which is very strong. And since years, though, they realized among the first the value of information to take a decision. So together with the University of Oslo, the ecosystem there, with the leadership of Equinor. Equinor is the state company, let's say, of Norway that extracts gas and oil. And they have developed, are still developing, what we call information modeling framework, which starts with the system model, as I told you before. So we arrived, that's why one of the reasons that I went there, is that we recognized both that we have the same vision, the same motivation. Start the development of data models, semantic data models, start with the system model. So they are using already they realized very quickly, as we may imagine, the value of standards. So these elements that you see here is part of this standard. These elements, I mean function, product, and location. Function, what is the function of the asset that you want you to have? Product is what is the physical realization that realizes this function, and the location is where this asset is to be placed to deliver the function. This is very important. If this asset, a pump, is under the sea, it's very different in the case that the pump is on the surface, on the earth. Okay? So this is the basic component. So the system block with the two terminals, that the terminals help to connect all these blocks together. And what we are going to do now in our next projects is to start developing knowledge graphs, data models, following part of this thing here, starting with semantic models, and automate as much as possible the creation of ontologies. This now is not automated. Humans create ontologies, but we have the trend to do it, to automatize this process to become cheaper and more precise and more standardized. To combine these two concepts in projects like this one, Ready. This slide is produced by Siemens, and in Siemens they understood also, they think in the same way. So we have in digital twins the product part and the production part, and the performance part. So these categories of digital twins that are not in one. So we have to make them work together. And in the product part, for example, you have simulations that help you to visualize what you are going to do, like the product models. You have simulation of the production, so elements of that was in the Airbus video also, when you simulate the production, the assemblies and all that stuff. And digital twins about the performance, what you measure from the controls and what you can do at the control level to improve the performance of the operations. So all these are different twins that have to be interconnected in order to have an optimal optimization at the end. And this is a project which is running, started a few months ago, which is about the product passport, digital product passport for digital twins along the value chain, circular value chain particularly, with various cases in various types of industry. This is something which is starting in November, where we're talking about data spaces and how semantic models can help the operations within the data spaces, sharing data or negotiating data, defining the IP and the ownership of data in the data spaces. So we have ontologies for that as well, and models, all in model-based. And this is the very new one, so we'll start in January, which is a manufacturing as a service, where you need, of course, all this concept with digital twins and cognition to take decisions about what manufacturer to use as a service, where, when, how you measure it, how you monetize it, and all that stuff. So there, it's not, yeah. And I think in my vision, so the final, let's say, use of digital twins as I see them evolving in the manufacturing, in the industrial context, is that in the shop floor, where you have the humans and the assets, so you have the activities, so you generate data with sensors that are stored in databases. At the same time, using appropriate standardized ontologies, you create knowledge graphs about whatever happens here. So this data are used in decision-making systems applying appropriate algorithms for contextualized reasoning. At the same time, you have the classical deep learning and machine learning algorithms that you can work on the data themselves. This is combined in the digital twin level, gathering results from there and from there. And this, in some cases, can develop a certain level of autonomy that allows the actuation of certain operations here. Not all of decisions taken by digital twins will be at the level and with the trust that will allow autonomous actuation of at the machines level. It will happen in some cases when we master very well the system, but I think this will go little by little, and in most of the cases humans will be involved. And these humans will be involved. How humans are involved is one of the key subjects of the next industrial revolution, the Industry 5.0, when you have sustainability, resilience, and human involvement. And humans means not only the well-being or the occupation of humans, but how humans work with systems. And this has to be also appropriate, organized appropriately by how human knowledge is communicated to system and vice versa. And then again, I believe that semantic technologies may help to go more correctly and deeper to that. So with that, thank you very much for your time and for your attention.